So children, now we'll start with the second part of the circles, that is chord properties of circles. These theorems are there. The last video was exclusively based on the finding of the general things about the circles. Now I'm saying theorem 15.1. which states that the straight line drawn from the center of a circle to bisect a chord which is not a diameter is perpendicular to the chord. Okay, this is the theorem, and see, for each theorem there is proof also, and proving is exclusively by the congruence only. So I've drawn a circle now, and now I'm drawing the chord. The theorem 15.1 and theorem 15.2 are reverse of each other. So I'm drawing a chord. After drawing a chord, I'll name it also, drawn through using scale. And see, center of the circle is O here, and I'm drawing a straight line from the center O using the scale. Okay, now this is the straight line that is drawn in the center, and this line is projected from the center towards the chord of the circle. Now theorem 15.1 and 2 are converse of each other. Let me adjust it properly. It should come like this as a chord only. Right now it will make a secant or tangent right now. Okay. And see, for this particular theorem also, like for proving part, you have to do some construction also. That OM should be drawn. So you have to join OA and OB. And what are OA and OB? OA and OB are basically your A is this point of the chord, that's the line segment, and the other end of the chord is B. Okay. Now what they are saying, we have to join OA and OB also, and we are joining it because we have to prove that the line OM is perpendicular to AB. The theorem states that the straight line drawn from the center of a circle from the center of a circle which is not a diameter. So you can have the line drawn from that center to diameter also, because the diameter is the biggest chord possible, but we're not doing this one. Here we are taking so this theorem is valid for all the chords but not the diameter. To bisect a chord, that's why in the bracket it has mentioned it is not a diameter. It will be perpendicular to the chord, is perpendicular to the chord, which is not diameter. So this particular criteria has to be ensured. You cannot see the same thing. This theorem is not valid for the diameter part. Okay, you can see this theorem is valid for all the chords except the diameter. And see, while proving so many theorems and so many questions, you'll be having the requirement of this same thing, a diameter, which is not a diameter. Is perpendicular to the chord. Okay. Now see, this is the chord, this is the center. We have joined the line from O to B and O to A. This is the point is M. M is the point where the line drawn from the center is touching the chord. Okay. So OAB is a chord which is not a diameter. Then what? OM. Can I say OM is what? The distance. OM is such that OM is perpendicular to AB. So OM is perpendicular to AB, we will get it. This is the result of. So this is what we have to prove. Now how will prove it? I am joining O to B and O to A. Then what you can say? So congruence only. By congruence we prove it. We have two triangles and we prove the triangles are congruent. If you prove the triangles to be congruent, can you say two angles will be equal? Which angles? OMA and OMB. So same angles will be there. So since they are equal, their sum equal to what? 180. So one angle equal to what? 90 degree. That's how we prove it. Okay. Two these are radii are equal. OB and OA are equal. And then how it comes perpendicular like that only. And we'll prove them congruent by SSS criteria. Which triangles? Triangles OAM and OBM. Already the two radii are equal. Then this OM is common. And the chord is being bisected by the line OM. So that is why AM and B will be equal. So by which criteria? By SSS criteria. One side is the radii, other side is the chord which is bisected, which is equally bisected by the line OM, and the common side is the OM line only, that is drawn from the center of the chord by SSS criteria. Easily you can prove. Then next theorem is theorem 15.2. This is converse of theorem 15.1. This is converse of theorem 15.1. Theorem 15.1. And see, in theorem 15.1 we are proving that it will be perpendicular, line drawn from the center to bisect the chord is perpendicular. Here what you will say? You will say the perpendicular will be bisecting the chord. The perpendicular to a chord. The perpendicular to a chord from the center of the circle. From the center of the circle bisects the chord. Okay, bisects the chord. Now what you can say? Let us draw the circle first. And then I'm drawing the chord. The setup of the diagram is same as like the previous theorem only. Only thing is what we are proving is the converse of the previous theorem. I have drawn the chord. Now I'm drawing the line from the center to the chord. Now this line will be initially perpendicular. In the first question, in the previous theorem, it was not perpendicular. We had got to prove that it was perpendicular. It was bisecting initially. Now here it will be perpendicular initially and it will bisect it later. Again, with the same concept of triangles, you can prove the congruence and prove that it is bisecting the chord. So initially it has to be perpendicular. Naming it A, M and B. Then I'm drawing line from O to M, O to A and O to B. What is given to us? Given that OM is perpendicular to AB. This we have already got from this. Next what? These radii are equal. OA and OB are equal because they are radii. Then have we got initially only this thing that OMA equal to OMB angle because they are right angles. So obviously we are proving it by RHS criteria. So being a right angle triangle and other two sides being equal, like we have done in chapter number 10. It is by RHS criteria. We can prove that AM and BM will be equal. I hope it is clear to all now. Now see, this congruence is proved by the RHS criteria, and this is converse of the theorem number 15.1. Both these things are used in the many questions. We will use it. So, like the previous question, it was initially equal. The chord was bisected, and then that is why that line was perpendicular to the chord. Now here is what the line is perpendicular, and that line is bisecting the chord. Next, we are taking the next theorem. It is theorem 15.3. Theorem 15.3. What does it say? Theorem 15.3 says equal chords of a circle are equidistant from the center. That means if the length of the chords are equal, their distance from the center will also be equal, but in the same circle we are talking about. Again, for this theorem also there is proof. The statement we are knowing now. Let us see how it is done. Through the figure also we will learn it. Drawing a circle now. Now I am drawing the chords freehand only. I will try to draw the chord with the circle, because the length of chords, if you are taking initially only equal, it will be, maybe it will not come geometrically correct, it can be, but again visually it cannot be correct. Okay, so we are taking the chord. We will try that. We will draw with scale first. We will draw in the first chord AB. By construction we can only show that how length we are fixing the length, but when we fix the length they will come too close to the circle center. That will be not very much fruitful in that regard. Okay, see, this is coming very close to the center now. So it's better we go with the freehand diagram only, the chord. Theorem we must know, and proving also we must know about it to do that one. Okay, otherwise it will look like a triangle on inside the chord, just inside the circle. Okay, though I have drawn the second one, but again it is looking like very close to the things, to the center, both the chords, and they look almost parallel only. And the actual figure that you draw on the book, they are not parallel actually. Okay. Drawing the second one now. Okay, it will go outside, and if you measure the length also, it will look like they are not equal in length. So that's why drawing it that way. Now visually only they will not look equal here. Okay, so I'm erasing this one. transposing this to the next page only. I'm taking a fresh circle, and now that only we are drawing the freehand diagram. The chord can be drawn like that also. Now I'm drawing the first chord, which is AB. Then second chord is CD. Second chord is CD. And we are given the initial condition that the length of chords is equal. What is mentioned? If AB equal to CD, that the length of chords are equal only initially. Then what will happen? We'll draw some line from the center. Center is O. And again, in this question, this theorem proving, we have to draw the construction. So construction is what? We are drawing OM perpendicular to AB and ON perpendicular to CD. So when they are drawn perpendicular, the foot of the perpendicular is M for AB and N for CD. So if AB equal to CD, then OM is equal to ON. That is equidistant from the center. That is what the theorem says. Now for proving it, again we will make two triangles by joining the O to A. Broken line and drawing, you can also draw broken line, and then O to C. Now we got two triangles. The triangles are OAM and OCN. OAM and OCN, yes. The two triangles are there. Initially only we have drawn two perpendiculars, that is the OM and ON. OM is perpendicular to AB and ON is perpendicular to CD. Can I say OA and OC are the radii? And since these two triangles are there, in which we are proving the congruence. Congruence you already are knowing also. Now see this one. You can say this AM equal to half AB. See, since this M is perpendicular to it, and this M is being perpendicular, which theorem we can use? M being perpendicular, it should be bisecting the chord. So this is theorem number 15.2. So M equal to half AB. By using the theorem number 15.2, then what we can say? We can say Cn equal to half CD. Again by using theorem number 15.2, which says that perpendicular from the center bisects the chord. So that is, so OM is perpendicular to AB and ON is perpendicular to CD. So Cn equal to what? Half CD. Again using your theorem number 15.2. And see, not only AM equal to half AB and Cn equal to half CD, AM and Cn also are equal. Why? Because AB and CD are equal. So that is how we have got the two sides being equal. That is construction is required here. Join OA and OC. So OM is perpendicular to AB and ON is perpendicular to CD. So you can say AM equal to Cn. Since AB equal to CD. Then what more? Scrolling it further. So these are equal. Cn and AM are equal. Just now we have proved using theorem number 15.2, and the length of chords being equal. The half also will be equal. What next? Now see here. Next is theorem 15.4. 15.4 is converse of 15.3. 15.3 was saying that equal chords are equidistant from center. 15.4 says if chords are equidistant from the center, they will be equal in length. So again, for the proving part, again same setup you have to use. That is, we will have a circle and there will be two chords. The distance of the chords will be equal, and for finding the distance we need to draw perpendiculars from the center. So what is the theorem saying? Chords of a circle which are equidistant from the center of the circle are equal, or will be equal. Length of the chords will be equal. So through 15.3 we have proved using the RHS criteria, because one angle was per right angle, and in theorem 15.4 also same criteria we are using. Let us draw the circle and the two chords A, B and C, D. Then I am dropping the perpendicular from the center O to M and O to N. And what is given to us? Given is that if the length of the distances are equal, that is, if O1 is equal to ON, then what will happen? Then you can say AB equal to CD. This is the theorem number 15.4. Again, drawing the dotted lines connecting O and A and O and C. These angles are perpendicular, we have drawn. And since they are perpendicular, we can say easily that what will be AM? AM equal to what? Half of AB. Using theorem number 15.2. And CN will be what? Half of CD. Using theorem 15.2. And then we have to prove what? We have to prove that AB and CD are equal. Same method we use. So next is theorem number 15.5. Theorem 15.5 says there is one and only one circle. There is one and only one circle. Only one circle. Circle passing through. There is only one and only one circle passing through. Three given, passing through. Three given non-collinear points. Non-collinear points. Non-collinear points. Okay, so this is a theorem here, and for this theorem we have got three corollaries also. These all theorems we will be using in one or the other way for proving congruence. So first is corollary 1. Corollary 1 says, in the plane of a circle, the perpendicular bisector of a chord of a circle passes through its center. In the plane of a circle, perpendicular bisector, the perpendicular bisector of a chord, bisector of a chord of a circle passes through its center. Of a circle passes through its center. Then what? Its center. Second is corollary 2. Corollary 2 states what? It states that. So in corollary 1 we will learn what? We learn that the plane of circle, the perpendicular bisector of the chord will pass through its center. And then corollary 2 is what? The perpendicular bisectors of two non-parallel chords will intersect at center. The perpendicular bisector of two non-parallel chords of a circle intersect at the center. Okay, of the circle. Next is what? This is your C. To learn it and use it, the questions for proving part will be using all these things, these theorems. Will be many questions also, it will be coming to you. Then what is corollary 3? Corollary 3 states that as there is one and only one circle passing through three non-collinear points, two different circles can meet at most in two different points. Let me write that. It says two different circles. See, because 3 has initial part got with 15.5 only. Initial part of corollary 3 is 15.5. So it says two different circles can meet at most in two different points. At most in two different points. Okay. What next now? We write it also, because that will make the corollary complete. As there is one and only one and only one circle one and only one circle passing through three non-collinear points. Okay, non-collinear points. That is the third corollary of theorem number 15.5. I hope it is clear to all. And these corollaries we have, these are the conclusions basically from theorem 15.5. And see, they have drawn that circle also, and they have shown, they have made a circle, they have made chords. One chord is AB, one chord is CB. Okay. Now we are taking the arc and chord properties of circles. This is helpful for theorem number this exercise 15.2. So what are arc and chord properties? Very short they are, but again they are used. The first thing that we learn in this is exams of equal arcs. Exams of equal arcs. Exams of equal arcs. Equal arcs. Which says that in equal circles, I think so in the previous lecture already I told you what are equal circles. If and only if they have equal radii, same radii, then they are called as equal circles. So this is for equal circles only. In equal circles or the same circle, if two arcs subtend equal angles at the centers or center, if two arcs subtend equal angles at the center, then we can say those arcs are equal. Then they are equal. So if angles equal, the arcs are equal. That means the arcs are only separating the angles, and in that circles have to be equal. Clear to all? Now next is what? We are drawing a circle now. And see, I am drawing an arc. Two circles are there and angles are equal in this. I am taking the same angle theta. One center is O. The arc is PQ. Other arc is AB. The angles I am naming theta 1 and theta 2. So if theta 1 and theta 2 are equal, we can say arc PQ and arc AB also will be equal. Make sure you remember the way how we are showing the arc. When we write the letters, we are showing a arc on the top of it. That is the representation of the arc. Then the converse also is true. Conversely, we can say in equal circles, converse is also true. If the circles are equal and if the arcs are equal, they subtend equal angles at the center. So for theorem 15.3.1, the exam of equal arcs. So if arcs are equal, this implies that equal angles subtended at the center. That's how you can say the converse of this theorem is. The exam is, not theorem, exam. Okay, now it should be clear to you now this. Next, theorem 15.6. Theorem 15.6. It says that in equal circles or in the same circle, equal chords cut off equal arcs. In equal circles, or in the same circle, equal chords cut off equal arcs. That means if length of the chord is equal, the arc will be, which will be cut off from that, the ends of that will be also equal. Previous exam was for the equality of angles through the equality of arcs. This is for the equality of arcs to the equality of the length of the chords. So two circles are drawn. The one chord is AB, other chord is CD. So what is theorem 15.6 here? To draw it properly. Okay. Other chord is CD. If the length of AB and CD are equal, then if AB is equal to CD, it means if the length of the chords are equal, what we can say, that the length of arcs also will be equal. This implies that arc AB with that symbol of arc, and then arc CD will be equal only when if the circles are equal and the length of the chords are equal. Okay. Next is theorem 15.7. It has got two corollaries also. Theorem 15.7. Theorem 15.7 says, and this is converse of theorem 15.6. 15.6 said what? That if chords are equal, the arcs will have equal length. So this will say what? If the arcs are equal, the chords are equal in the equal circles. So this is converse of theorem 15.6. Converse of theorem 15.6. In equal circles or in the same circle, in equal circles, if two arcs are equal, arcs are equal then their chords are equal. Then their chords are equal. Okay, that's what they are saying. So 15.7 is converse of 15.7. This also has got two corollaries, corollary 1 and corollary 2. So let's draw it and see it to the diagram. I'm drawing two circles. These circles are assumed to be equal. Okay, so they are equal circles, means the radii is same. Drawing the arc, the first arc is PQ. Second arc I am drawing in this second circle, which is having same radii, it is RS. So if PQ and RS are equal, the length of the chord PQ and RS will be equal. So if arc PQ equal to arc RS, this implies that PQ is equal to RS. PQ and RS are the chords for the circle. Next what? So you can draw using this circle also. Center we will take, again we will take two triangles. Center is O. You can take O dash in the second one and do congruence. See, OP equal to OQ, OR equal to so this circles have to be equal. That is the radii are equal. Okay. If arcs are equal, we can say that what the angles which are included will also be equal. So it is SAS criteria. By SAS criteria, we can say that it is like that. Now corollary 1 and corollary 2. Corollary 1 and corollary 2. Corollary 1 and corollary 2 is what? First corollary is equal chords of the same circle. equal chords of the same circle subtend equal angles at the center. So, or you can say equal chords subtend equal angles at the center. At the center. This is the first corollary from the theorem 15.7. Corollary 2 is equal angles at the center make equal chords in equal circles or in the same circle. So the corollary 1 is also for the equal circles only. In equal circles. Okay. This is also for equal circles only. In equal circles. Corollary 2. In equal circles or the same circle, equal angles at the center or centers make equal chords. Equal angles at the centers make equal chords. Make equal chords.